Hi guys, my name is Ihab.
And this is Shabir.
We both are going to talk today about optical measurement techniques and specifically LIDAR. LIDAR is a surveying method that measures distance to a target by illuminating the target with pulsed laser light and measuring the reflected pulses with a sensor. It uses laser beams in the ultraviolet visible spectrum and the infrared region of the electromagnetic spectrum.
Light is known as the electromagnetic spectrum in scientific terms. As you can see in the top image, the electromagnetic spectrum covers electromagnetic waves with frequencies ranging from below 1 Hz to above 1025 Hz, corresponding to wavelengths from thousands of kilometers down to a fraction of the size of an atomic nucleus. As you can see on the image on the right, each electromagnetic wave has its own usefulness. On one end of the spectrum lies radio waves, which are used to transmit information across distances in radio communication systems such as radio broadcasting and television, which is followed by microwaves that are used in radar and Wi-Fi systems, and thereafter infrared, which are normally used in TV remote devices. While on the other end, the UV radiation is highly useful for sterilization, disinfection, and the X-rays are famous for X-ray scans, and gamma rays are very useful for removing decay-causing bacteria from foods. Visible light, which we simply refer to as light, is a small portion of the electromagnetic spectrum which is visible to the human eye and is responsible for our sight. Visible light is usually defined as having wavelengths in the range of 400 to 700 nanometers and is in between the infrared and the ultraviolet regions. All waves in the electromagnetic spectrum have a velocity of 3 to 10 power 8 meter per second.
The phenomenon of light which LIDAR takes advantage of are reflection of light and Doppler effect. Firstly, let's talk about reflection of light. Reflection is when light bounces off an object. It can reflect at the same angle as it hits the surface if the surface is smooth, or there might be even diffuse reflection in lots of different directions when the surface is rough. Most of the things we see are because of light from a source that is reflected off the object. The Doppler effect is the change in frequency or wavelength of a wave in relation to an observer who is moving relative to the wave source. The reason for the Doppler effect is that when the source of the wave is moving towards the observer, each successive wave crest is emitted from a position closer to the observer than the crest of the previous wave. Therefore, each wave takes slightly less time to reach the observer than the previous wave. Hence, the time between the arrival of successive wave crest at the observer is reduced, causing an increase in the frequency. While they are traveling, the distance between successive wave fronts is reduced, so the waves bunch together.
LIDAR, light detection and ranging. LIDAR is a remote sensing method that uses laser to measure elevation like ground, forests, and buildings. LIDAR uses ultraviolet, visible, or near-infrared source to sense objects. Light energy emitted by LIDAR system is known as pulse. Light reflected from ground or object is known as return. This means the LIDAR system sends a pulse of light and it waits for the pulse to return. It measures how long it takes for the emitted pulse to return back to the sensor. In the end, it gets a variable distance of the objects. Actually, this is how LIDAR got its name: light detection and ranging. Like sonar uses sound waves to map things, radar uses radio waves. A LIDAR, on the other hand, uses light sent out from a laser. A LIDAR scans the ground from side to side as the plane flies. Because of this, it covers a large area. While some pulses will be directly at nadir or a straight line, most pulses travel at an angle. Airplanes, unmanned aerial vehicles, and helicopters are the most commonly used platforms for acquiring LIDAR data over broad areas. There are different ways to collect data using LIDAR: from ground, from plane, or from satellite.
The actual calculation for measuring how far a returning light photon has traveled to and from an object is quite simple. Distance equals speed of light times time of flight divided by 2. The LIDAR instrument fires rapid pulses of laser light at a surface summed up to 150,000 pulses per second. A sensor on the instrument measures the amount of time it takes for each pulse to bounce back. Light moves at a constant and known speed, so the LIDAR instrument can calculate the distance between itself and the target with high accuracy. By repeating this in quick succession, the instrument builds up a complex map of the surface it is measuring.
There are 4 main components of the LIDAR. Let's start with laser. Laser beams have a Gaussian beam profile and the beam divergence angle is very small compared to other light-based signals. The formula for beam divergence angle theta is shown in this slide. The main advantage is that the contact point of the measurement is very small and hence we can get very precise measurement and displacement maps.
Now we move on to scanner and optics. The speed at which images can be developed is affected by the speed at which it can be scanned into the system. A variety of scanning methods are available for different purposes, such as azimuth and elevation, dual oscillating plane mirrors, dual axis scanner, and polygonal mirrors. The type of optic is important because it determines the resolution and range that can be detected by a system. Photodetector and receiver electronics. The photodetector is a device that reads and records the backscattered signal to the system. There are 2 main types of photodetector technologies: solid-state detectors such as silicon avalanche photodiodes and photomultipliers.
Lastly comes navigation and positioning systems. When a light detection and ranging sensor is mounted on an aeroplane, satellite, or automobiles, it is necessary to determine the absolute position and the orientation of the sensor to maintain usable data. GPS provides accurate geographical information regarding the position of the sensor, and an inertial measurement unit records the accurate orientation of the sensor at that location. These 2 devices provide the method for translating sensor data into static points. There are many types of LIDARs, and the most common ones are airborne and terrestrial.
There are several factors affecting the performance of a LIDAR, including range and sensitivity. The sensitivity of a LIDAR is directly related to the intensity and scattering of the reflected beam. Higher frequencies of beams have higher intensity and power and have greater chances of reflecting back to the LIDAR, thus providing more data sets for mapping purposes. However, the footprint of the laser beam, that is, the area covered by the laser, is lesser for higher intensity beams. Even when the frequency of the laser is kept constant, increasing the intensity would mean lowering the beam divergence angle, thus covering less area. We have to decide according to the mapping requirements for these cases. Smaller footprint would mean detailed local mapping, and larger footprint is needed for complete ground sampling and for more interactions with multiple vertical structures.
LIDAR resolution, or number of pulses per unit area, is also a critical aspect. Current systems are capable of producing around 20 pulses per square meter. It is mainly determined by the aircraft speed, flying altitude, field of view, and rate of pulse emission. Higher resolutions allow the surface and the features on the surface to be better resolved, but at the cost of greater datasets and larger processing times. Lastly, we can take advantage of the intensity of the reflected light to identify the surface cover, since the amount of reflection varies with surfaces. Increasing the accuracy of the process is quite simple. We need to remain close to the mapping target and reduce the beam divergence, which is impossible for some cases.
LIDAR as a remote sensing technique has several advantages. Some of them are high accuracies, high point density, large coverage areas, and the ability of users to resample areas quickly and efficiently. This creates the ability to map discrete changes at a very high resolution, cover large areas uniformly and accurately, and produce rapid results. These features help in forest and coastal change mapping. LIDAR is also the main component for self-driving vehicle. It enables a self-driving car to view the surroundings with the help of its mapping features. LIDAR beam's short wavelength helps in modeling pollution. This helps to image the matter which is of the same size or larger than the wavelength. So, LIDAR can detect pollutant particles of carbon dioxide, sulfur dioxide, and methane. This information helps researchers to create pollutant density maps of the area, which can be used for better planning of the city.
Alright guys, that's enough of LIDAR for today.
Until next time, this is Ihab and Shabir signing out.